Let us consider determination of the Butterworth polynomial for a particular example when the value of order is equal to 2. We are aware that the transfer function for a normalized filter can be represented as Hn of s is equal to 1 divided by pi of s minus sk, where sk is the poles in the rectangular form. We favor only the left half poles because they are considered to be stable. The Butterworth polynomial can be expressed as Bn of s. Bn of s denotes the polynomial for order n. Now the example here, we are taking n value to be equal to 2. This yields the total number of poles as 4, which is twice of n. 2 of the poles will lie on the right half of the complex plane and 2 of the poles will lie on the left half. Now let us determine the value of the poles. The first pole is at k is equal to 0. The value becomes S0, which is equal to magnitude 1 with a phase angle of 3 pi by 4 by applying the formula for theta k. Solving for this value and converting it from polar to rectangular form yields the result minus 1 by root 2 plus j 1 by root 2. Similarly, when you determine the second pole for k value equals 1, the magnitude is 1 and the angle is 5 pi by 4. The separation between the two poles happens to be equal to pi by n. In this case, n value is 2, hence the difference between the two is pi by 2. Converting this into rectangular form yields the answer minus 1 by root 2 minus j 1 by root 2. The same fashion we can proceed to compute the value of S2 and S3. S2 and S3 is not considered here because the right half poles are considered to be unstable. We have computed the values which lie on the left. Now, inserting it in the Butterworth polynomial Bn of s, for n is equal to 2, the expression becomes B2 of s, and we are considering the two roots S0 and S1. Therefore, substituting the value of S0 and S1 in rectangular form, we get the value as shown. In order to simplify this expression, we can assume the value of S plus root 2 to be A and the value of J 1 by root 2 to be equal to B. We are aware that the expression now is in the form of A plus B into A minus B, which yields the solution a square minus b square. Therefore, taking the value of a square minus b square and simplifying, we get the value as s square plus root 2 plus root 2s plus 1 by 2. So, summing it all up and simplifying, we get the answer as s square plus root 2s plus 1. On similar lines, the Butterworth polynomial or the denominator in this particular expression can be solved and obtained for different values of order. Using the same method, below we have listed out the values of Butterworth polynomial for different orders. The expression for order 1 is as simple as s plus 1. You will have primarily one pole on the LHP and one pole on the RHP, as illustrated here on the complex plane. The horizontal axis is the real axis, the vertical axis is the imaginary axis indicated by j omega. Therefore, we have one pole called as S0 and one pole called as S1. Both of them lie on the real axis, and hence this particular pole on the LHP has a value that is -1. So substituting in the equation would give you a simple Butterworth polynomial as s plus 1. We have already evaluated the Butterworth polynomial for order 2, which gives you the expression as s square plus root 2s plus 1. Similarly, the Butterworth polynomial for order 3 is given as s square plus s plus 1 into s plus 1. For order 4, it is s square plus 0.76536 s plus 1 into s square plus 1.84776 s plus 1. For the fifth order, it is s plus 1 into s square plus 0.6180 s plus 1 plus multiplied by s square plus 1.6180 s plus 1. So this way, we can determine the Butterworth polynomials for order 1 to 5, and a similar procedure can be used to compute for other orders also. Next, we discuss about the topic which is called as frequency transformations. The method of designing a Butterworth analog filter involves designing a prototype first. A Butterworth prototype is one whose edge frequency for the passband should be equal to 1 radian per second. Now converting this normalized prototype into the corresponding low pass, high pass, band pass and band stop can be achieved by using some simple conversion rules as illustrated in the diagram. This process is called as frequency transformation, or it's also called as frequency translation or spectral transformation. In the first case, we can observe the value that is considered. Initial conversion is for low pass to low pass. So here we are converting from a normalized low pass to a low pass filter which has the edge frequency which is something other than 1. The parameters Kp and Ks illustrate the gains at the two edge frequencies respectively. Hn indicates it's for a normalized or a prototype filter. We observe that the edge of the passband is at 1 and the stop band edge frequency is indicated as omega s. If we make the replacement of s by s divided by omega u, where omega u is the desired frequency, u is the desired frequency, this substitution has to be performed in the transfer function. Other words, we are going to determine HA of j omega from Hn of j omega. Alternatively, the transfer function for this will be called as HA of S, and HA of S is obtained by making a substitution in Hn of S. And the substitution is of the nature that S should be changed to S divided by omega u. So this is referred to as the low pass to low pass transformation. Now we observe from the diagram that the passband edge frequency has now changed from 1 to omega u. At the same time, omega s will also be changed and is indicated by a new frequency called as omega s dash. Backward design equations are also given for your reference. The meaning of backward design is if you want to convert from the actual frequency response to that of the prototype frequency response, the value of omega s can be determined from omega s dash using this transforming equation. In other words, we are aware that omega u has to be changed to a value 1, which can be accomplished by dividing by omega u. Similarly, when omega s dash is divided by omega u, you yield the value which is called as omega s. A similar procedure could be adopted to find the transformation for low pass to high pass, except that the transformation is slightly opposite to that of a low pass filter. Here, the transforming equation is s being replaced by omega u by s. Please note that the numerator and denominator are interchanged in this case. When you are converting from the normalized low pass filter to that of high pass, we observe that the bands of low pass and high pass are opposite. In other words, previously where there was a pass band, now you will find a stop band, and previously where there was a stop band, now the pass band will be found. Therefore, the frequency which appears first is designated as the stop band. Now, not to confuse with the value of omega s, we indicate this value as omega s dash. And the upper frequency is called as omega u. Therefore, the transformation from low pass to high pass is substitution of s with omega u by s in the normalized transfer function. On similar lines, the backward design equation is given as omega s equals omega u divided by omega s dash, which once again stems from the fact that omega s dash is changed to the value 1, which can be possible by dividing it by omega s dash. And omega s is computed as omega u, also which is divided by omega s dash. So this will be the backward design equation which helps in calculating the stop band edge frequency. Now, coming to the case where we are solving for the low pass to band pass transformation. Band pass filters are a combination of high pass and low pass. First, we encounter the stop band. In between, we have a pass band, and once again, we have the stop band. Therefore, the total number of edge frequencies we have will be 4 in number. The edge of the stop band is denoted as omega 1 and omega 2. The edges of the two pass bands are indicated as omega L and omega U. Now, to convert from the normalized low pass to the band pass, we use the transforming equation as S being replaced with S square plus omega U times L divided by S into omega U minus omega L. In this equation, we can identify that the term here is called as omega naught square, where omega naught is called as the center frequency. The term in the denominator is the difference between the upper edge of the pass band and the lower, and is termed as the bandwidth. Therefore, the expression can be remembered as S square plus center frequency square divided by S times the bandwidth. In this case also, the backward design equation to determine the value of omega S from the specifications is as follows. First, we determine a quantity called as A, which is given by minus omega 1 square plus omega L times omega U divide by omega 1 into omega u minus omega L. And B is found in a similar fashion as omega 2 square minus omega L omega u divided by omega 2 into omega u minus omega L. Once A and B is found, we calculate the value of omega s to be the least among A and B. So we are using minimum of magnitude of A and magnitude of B. Irrespective of the sign of the answer is always positive. So among the two, we take the least and assign it to the value called as omega s. A similar transforming step can be performed if you are going for low pass to band stop. Once again, band stop is opposite in nature to that of band pass. We encounter the pass band initially, then comes the stop band, and once again you have the pass band. We use the same notation for the edge frequency of the pass band, and we use the same notation for edge frequency of stop band. The stop bands are denoted as omega 1 and omega 2. The pass band is called as omega L and omega u respectively. The frequency transformation step can be considered to be the opposite of that of band pass. The numerator in the first equation becomes the denominator in the second case. So hence this equation can be remembered in a very simple way. Also, the equations that are used for these two cases could be considered to be almost opposite to that of the one for band pass. Numerators, denominators, we observe are swapped. Let us now discuss about the design of low-pass Butterworth filter. The meaning of design here is to determine the transfer function for a normalized Butterworth filter. In order to obtain the transfer function, we have to find two important parameters. One is the order of the filter. The order is indicated by capital N. And the second important parameter is omega c, which is cutoff frequency. So if we are able to find the order and cutoff frequency, then we can proceed to go for the transfer function called as h of s. First, to carry out the design, we start with the frequency domain specifications. The frequency domain specifications are as follows. We are aware from the frequency response that the parameters given for design are Kp, Ks, omega p and omega s. Kp is the gain in the passband. Ks is the gain in the stop band. Omega p is called as the passband edge frequency, and omega s is the stop band edge frequency. The same is illustrated in the case of a low pass filter. The maximum value of gain is said to be 0 in the dB scale. Your vertical axis is in dBs because we observe it is 20 log of h of j omega, where h of j omega is the frequency response. Now, the gain at the passband edge frequency omega p is termed as Kp. The gain at the stop band edge frequency omega s is called as Ks. Therefore, mathematically, the range of values which lie in the passband are between 0 to Kp. Therefore, we can write 20 log of magnitude of h of j omega. It lies between the maximum value Kp and the minimum value 0. In fact, the reverse is true. Kp is a smaller number and 0 is larger because we are dealing in the dB scale. Kp value will be negative and 0 is more than a negative number. The value of frequency which lies in the pass band is between 0 to omega p. So we are considering frequency value less than or equal to omega p. Similarly, for the stop band, a frequency greater than omega s is considered to be the stop band. In that region, the value of gain will be less than or equal to the value which is called as ks. Using these specifications, we shall proceed for determination of order. As we had mentioned, the design of a low-pass filter means to determine the transfer function, which is Hn of s, which has the form as shown below. Now here we have to have a knowledge of the order and cutoff frequency to be able to correctly do that. Let us arrive at an expression for the order and then the expression for cutoff frequency. To start with, we take the magnitude response of a low-pass Butterworth filter, which is given by magnitude of h of j omega, which equals 1 by 1 plus omega by omega c to the power of 2n whole raised to 1 by 2. This equation, let us number it as 1. Taking 20 log on both sides of equation 1 to convert it to dBs. Therefore, the left hand side becomes 20 log of magnitude of h of j omega, which is denoted as k, where k stands for a gain. So k here represents a gain which is measured in terms of dB. Coming to the quantity on the right hand side, once you apply the log, we convert this denominator quantity, taken it into the numerator part. The sign of the exponent changes from plus to minus. And once the minus sign is brought out, the 20 log, it becomes negative. So once again, if the denominator quantity is shifted towards the numerator, then the power is changed from plus to minus, and that minus, if it is brought forward before the log, then the sign becomes minus 20 log of the quantity. Next, 1 by 2 is also brought forward, and simplifying, the expression becomes minus 10 times log of 1 plus omega by omega c whole to the power of 2n. Therefore, we have found the expression to indicate the gain which is in terms of dB. Let's number this equation as equation number 2. Now, in equation 2, let us make a couple of changes. From the figure, we have observed that when the value of frequency omega is equal to omega p, the value of gain will be equal to kp. Therefore, let us do the substitution. Omega is equal to omega p and k value is equal to kp in equation number 2. Therefore, the result of the substitution can be observed here. The expression becomes kp is equal to minus 10 times log of 1 plus omega p by omega c whole to the power of 2n. Once again, omega is replaced with omega p and k is changed to kp. Now let us simplify and bring it to a form which is understandable to us. So rearranging the terms and trying to get an expression for omega p by omega c whole to the power of 2n will give you the result 10 raised to minus kp by 10 minus 1, and this equation is numbered as 3. The steps of the simplification can be discussed here. The first step would be to eliminate the log. We have a step called as anti-log. First, you bring the minus 10 to the denominator position. Then you take anti-log of that quantity. Anti-log of that quantity will become 10 to the power of minus kp by 10. The anti-log will eliminate the log. So once eliminated, you have the simple term 1 plus omega p by omega c to the power of 2n. Since we require omega p by omega c to the power of 2n, the value 1, when it is shifted to the other side, it becomes minus 1. So these are the simplification steps which can be easily used to arrive at this equation called as equation 3. In a similar fashion, in the equation 2, when we consider the frequency omega equals to omega s, we are aware that the gain is equal to ks. And we get a similar result as we had got in equation number 3. The changes are, in place of omega, we have omega s, in place of k, we have ks, and the equation simplifies to a form as shown in equation number 4. So previous equation 3 was in terms of kp and omega p, equation 4 is in terms of ks and omega s. Now let us perform the division. Equation 3 divided by equation 4 will cancel off the common term which is omega c in the denominator, and we get the ratio omega p by omega s to the power of 2n, which is a ratio of two quantities 10 raised to minus kp by 10 minus 1 divided by 10 raised to minus ks by 10 minus 1. Now, in order to solve and get the value of n, we have to apply log so that n can be brought outside. Taking log on both sides, we get 2n times log of omega p by omega s, which is equal to log of the ratio. Solving for n, we get the result as shown here. The result will be equal to log of 10 to the power of minus kp by 10 minus 1 divided by 10 to the power of minus ks by 10 minus 1 divided by 2 times log of omega p by omega s. This is a very important equation which is going to help you to find the order of the particular filter. Now that we have understood how to find the order of the filter, let us proceed to obtain the cutoff frequency. The cutoff frequency can be determined in a couple of ways by using the results that we already have. One of the results is equation 4. We observe that if we solve equation 4 and we can find the expression for omega c. This omega c will be on the basis of the value of ks and omega s. On similar lines, you can solve for equation 3 and calculate the value of omega c. The solution is done here just for your reference. So to get the value of omega c here, number 1, we have to eliminate the power which is 2n, which is possible by taking the power 1 by 2n on both sides of this equation. So doing that will result in the value omega p by omega c equals to the quantity 10 power of minus kp by 10 minus 1 whole raised to 1 by 2n. Then taking omega c to the other side, the quantity on the right will become the denominator for omega p, and you get the result as omega p by 10 to the power of minus kp by 10 minus 1 whole to the power of 1 by 2n. This is one expression, and equation 4 will yield a similar looking equation except for the fact that in the numerator you will have the frequency for the stop band and the gain will also be a stop band gain. Therefore, the expressions for omega c can be calculated as follows. The cutoff frequency omega c can be found. Number 1, first case. Suppose we want to meet the passband requirement exactly and do better than the stop band requirement. The cutoff frequency omega c is selected from equation number 3, and already we have discussed the result of that. It is omega c being omega p divided by 10 to the power of minus kp by 10 minus 1 whole to the power of 1 by 2n. Now what do you mean by meeting the passband requirement exactly? So suppose in the problem statement kp value is equal to minus 10 dB, we should get an exact value equal to minus 10 dB. And what do you mean by bettering the stop band requirement? Suppose the problem states minus 20 dB, you can get a value which is minus 22, minus 24. Means the larger the attenuation in the stop band, better it is for us in terms of the response. I hope this statement is clear. If we wish to meet the stop band requirement exactly, so this time in case 2, we want to match the parameter Ks exactly and do better in the pass band. For this, we have the equation which is arrived from equation number 4, and it's a similar looking equation except for the fact that omega p changes to omega s and kp changes to ks. So we have already discussed the procedure for finding this equation, and this is numbered as equation 6. Alternatively, we can use the average or arithmetic mean of the two cutoff frequencies arrived from the two steps. Then in that case, the response will do better in both the bands. Thank you all.